the bistable equation. Okay, so let's just start by introducing the bistable equation, and then you can watch a lecture on it.
Zach.
Yeah.
So when it has sort of fronts on both sides, like we would have in this case, how can we see that from the phase plane analysis on the previous slide?
That is, yeah, that's not captured by the phase plane analysis because it's not, it's technically, that is not a traveling wave solution. A traveling wave solution is strictly, you have some shape on your free boundary domain and it just moves with constant speed. If this thing spreads out, right, you have a growing blob, right? You don't have something that's just shifting to the right or shifting to the left. So you have to remember that the solutions that we get from this, they are sort of long time limit, sort of steady state type solutions, right? They're steady state in the traveling wave coordinate, right? So traveling wave analysis gives you intuition for this, but it will not give you the exact form of this evolution. But it will tell you that this should evolve to some traveling front type solution. And once these front edges are far enough apart, you can just sort of cut them in half and say, for all intents and purposes, the back of this front is essentially the same value throughout, right? It doesn't dip back down later because the diffusion kernel is not going to reach very far. Okay. Any other questions? Okay. So let me just, I'll just introduce bistable equation and then you can watch the lecture. Okay, so bistable equation. These are fairly ubiquitous in biology, chemistry, physics, some material science. And so just like the Fisher's equation, the bistable equation is built on a canonical bistable ODE. So I'll probably just have time to sort of talk us through this, okay? So U prime equals U times 1 minus U squared, okay? I think I'm doing this right, yeah. So if you've had any dynamical systems in your background, maybe you've seen this before, or bifurcation theory. This is often called the normal form of a pitchfork bifurcation. You've seen this in physics classes. You may call this the double potential well model. And there's some very nice ways to represent this. If we do a stability analysis, right, the equilibria of this equation are at 0, 1, and -1. If we look at the stability of these equilibria, they're given by f prime of u, which is equal to 1 minus 3u squared, okay? So f of u, or sorry, f of 0 is equal to 1, and f of plus and minus 1 is equal to -2. So this fixed point is unstable, and this fixed point here is stable, right? If you like, you can think of, f prime. This is like the one eigenvalue of that steady state, right? You don't remember that from ODE. So let's draw a phase line. So what we have here then is we have a steady state here, a steady state here, a steady state here. If I start here in U, I flow to the left, I flow to this fixed point. If I start here, I flow to the right, I flow to this fixed point, okay? Now, one thing that you can draw is what's called the potential function associated with this. So if we think of u prime as like minus d something I'll call we'll call it capital U du, if that's equal to u1 minus u squared. This is essentially saying u prime should flow down a gradient. If I draw the function that allows me to flow, whose gradient I'm flowing down, that is my potential function, okay? So in this case, this implies that my potential function, u of u, is equal to u to the fourth over 4 minus u squared over 2. So I can draw u as a function of little u, and it's going to look like this, okay, where essentially my, sorry, I didn't plan this well. My minimum here, right, is my u equals -1. My minimum here is u equals +1, and my maximum here is u equals 0. So if you think about u prime essentially enacting some sort of a gradient descent, then this is like I have a ball up here, and when it's this side of the peak, it's going to roll down to this valley here. When I have a ball here and it's to the left side of this peak, I'm going to roll down to this valley here. Okay, so this is a common model that's used. It's comes up a lot in, like, stochastic dynamics and things like that. I'll probably touch on it in asymptotics next semester. Okay, so this is our double potential well. Okay, so if you just have one of these systems, right, and you don't have any noise, it's pretty boring. You roll to the bottom of a well, you stay there. But imagine now that you couple a bunch of these systems together, right? If a neighboring point has its particle in a positive potential well, and then the other one has it in a negative potential well, you're going to have a tension between two neighboring states, right? So this, you could think of this as magnetic interactions, right? You sort of see things like this. It's not quite the same, but in the Ising model, and you see this a lot in biology, like electrically active cells. If you have, cardiac cells, one can be electrically active, the other's inactive. If they're coupled together, one will, potentially switch on another. Okay, so then that introduces interactions, and you don't just get this sort of boring, quiescent states. And obviously, we're going to show that you can get traveling waves in the context of this model. So to see all that, you have to watch the recorded lecture. We're out of time for now. Any questions so far on this, or anything else that we talked about today? Okay, I've tried to keep the pacing not too fast, because I know this is very, very different stuff. Okay, so for Monday, I'm happy also just to answer homework questions if the class as a whole has some. But yeah, I was thinking we'll do a couple practice problems with traveling waves, just to nail some of these points home. Cool. So look for that recorded lecture. It should be up probably by the end of the day, and then I'll post this too. All right. Well, that's it for today. Have a good weekend.
Thank you.
Thanks, Zach.